Hello everybody, I am Olivetti and I'm going to talk about lower bounds in the distributed setting. This is a joint work with Alkida Balliu, Sebastian Brandt and Fabian Kuhn. I will start by presenting the model of distributed computing that we consider. Then I will present a family of problems on which we prove some results, then the results themselves, and then I will try to explain the journey that took us here and some ideas behind the techniques that we use. Let's start by introducing the model. All the results presented in this talk hold in the local model of distributed computing. In this model, we have a network that is modeled by a graph, where nodes represent computing entities and edges represent communication links. We will denote with n the number of nodes in the graph and with delta the maximum degree. In this model, we assume that messages can be arbitrarily large, and also we do not restrict the local computation. Hence, this is a very strong model, and this means that if we prove lower bounds in this model, then they hold in weaker settings as well. In this work, we proved results for a large family of problems that are interesting in the distributed setting. This family contains some natural problems, but also many problems that have no real intuitive meaning. So I am going to present a nice subfamily of problems for which we obtain lower bounds in this work. We call them alpha are defective C-colored beta ruling sets. In this problem, nodes can either be colored or uncolored. The graph induced by colored nodes must be colored with an alpha are defective C coloring, and uncolored nodes must have a colored node at distance at most beta. Alpha defective C coloring just means that the nodes are colored, and some neighboring nodes may have the same color, and each subgraph induced by nodes of the same color must have its edges oriented such that the out degree is at most alpha. For example, the picture shows a 2 defective 2-colored 2 ruling set. In fact, you can observe that every uncolored node, that is white nodes, have colored nodes at distance at most 2. And then you can see that the graph induced by red nodes have out degree at most 2, and the same holds for blue nodes. For these problems, we proved lower bounds which turned out to be tight. This is a very nice family of problems. In fact, we directly get many lower bounds for very different problems. For some value of alpha, C and beta, we obtain problems that have already been widely studied in the distributed setting and for which the exact complexity is known, while for other values we obtain problems that are still very interesting and widely studied, but for which the exact distributed complexity was not known. In fact, our work gives a unified proof for both existing and new results. So let's see some examples of problems that are included in this family. By setting alpha to 0 and C to 1, we get that colored nodes must form an independent set, and uncolored nodes have distance at most beta from the nodes in the independent set. This problem is called 2 beta ruling sets, and we will later see why this problem is extremely important in the distributed setting. And if we set beta to 1, we obtain the MIS problem, because by setting beta to 1, we get that nodes are either in the independent set or they have at least one neighbor in the independent set. If, on the other hand, we set beta and C to 1, we obtain lower bounds for bounded out-degree dominating sets, which are a variant of dominating sets that have been studied in the distributed setting. Instead, if we set beta to 0, we get that all nodes must be colored, and hence we obtain lower bounds for alpha defective C colorings, which are an important primitive that has been used to solve other variants of the coloring problem. And if we set alpha to 0 and C to delta, we get a lower bound for the delta coloring problem. Instead, if we set alpha equals to delta minus 1 and C equals to 1, we get that all nodes have the same color, and the orientation of the edges is such that all nodes of degree delta have at least one incoming edge. This is a problem that is very famous in the distributed setting, and it is called singless orientation. Here are some concrete results that we obtained. For MIS, we proved that unless we spend a high dependency on n, this problem requires a number of rounds that is linear in delta, even on trees. And if we express this bound solely as a function of n, we obtain a lower bound of omega of log n over log n, which turned out to be tight on trees. Similarly, for ruling sets, we obtained tight lower bounds as a function of delta, and tight lower bounds as a function of n on trees, for a large range of beta at least. Then we also managed to exactly characterize which variants of arb defective coloring can be solved in O of f of delta plus log star n for some function f, and which of them require omega of log base delta of n. So we exactly characterize which variants are in some sense easy and which of them are in some sense hard. What is shown here are just a few examples of the results that we got, but the family of problems for which we proved lower bounds actually contains many more problems than just this one. So let's now see where the journey started and why the title talks about delta coloring. In the rest of the talk, we will see how the delta vertex coloring problem is strictly related to many other symmetry breaking problems that have been studied in the literature in the distributed setting, such as dominating sets, MIS, ruling sets, and arb defective colorings. Also, we will see how delta coloring is related to questions regarding complexity theory, and in particular to an open question regarding a class of problems that has been studied a lot in the distributed setting, called locally checkable labelings. Let me remind you briefly what a delta coloring is. We have a graph, and delta is the maximum degree of the graph. We want to color the nodes with delta colors, that is, assign to each node a color from a palette of delta colors, such that the neighboring nodes have different colors. In the example, delta is 4. Let's start by talking about how delta coloring is connected with distributed complexity theory. In the distributed setting, there is a class of problems that has been studied a lot, and is the class of problems called locally checkable labelings, or LCLs, that are informally the class of problems for which we can check if a solution is correct by inspecting the local neighborhood of each node. For example, the vertex coloring problem is an LCL because we can check if a solution is correct by checking that each node has a color that is different from the one of the neighbors. There are some technical details that I'm omitting here because LCLs are not the full class of locally checkable problems, but actually a restriction of it. But let's ignore this for now. People studied LCLs a lot in the distributed setting, and now we have this beautiful complexity theory built on top of them. For example, we know that some complexities are not possible at all for LCLs in the local model of distributed computing. For example, there are no LCLs that have a complexity that is strictly between constant and log of log star n. So all these orange parts represent complexity gaps, while blue dots represent complexities that actually exist. But there are still some open questions, and for example, there is a very specific region where we don't know exactly what happens there. And in particular, we don't know if there are problems that have randomized complexity strictly below log n, and at the same time deterministic complexity strictly above log n. And delta coloring is a problem that is a candidate to be in this region. And for this reason, researchers really try to understand the complexity of this problem. So this is where the journey actually started. Some people conjectured that this unknown complexity region is actually empty, and that would imply that for delta coloring, there must exist an algorithm that is faster than the currently best known one. So at first, we tried to improve the best deterministic algorithm for delta coloring, and we observed that the best algorithm uses as a subroutine an algorithm for a different problem called alpha-beta ruling sets, which is a generalization of maximal independent set that is used a lot in the distributed setting as a subroutine. So we tried to improve the complexity of ruling sets and to find faster algorithms. And we failed. For this reason, we started thinking about lower bounds, and in particular we wanted to prove that distributedly compute a ruling set cannot be done too fast. And as we have seen, it is indeed the case. And this implies that in order to solve delta coloring faster, entirely new ideas are required. While our lower bounds hold for a large class of problems, we actually started considering just ruling sets. So let's see how they are defined and some properties about them. An alpha-beta ruling set is a subset of the nodes of the graph such that the distance between each pair of nodes in the set is at least alpha, and each node not in the ruling set has a node in the set at distance at most beta. For example, in the figure is depicted a 2-3 ruling set, where the nodes in the set are the blue ones. You can see that the set is independent and that all white nodes have distance at most 3 from blue nodes. The family of ruling set problems includes a classical graph problem that is the maximal independent set problem. And please note that I am talking about maximal independent set and not maximum. And let me briefly show how the parameters alpha and beta play a role in the complexity of ruling sets. As already mentioned before, a 2-1 ruling set is equivalent to the maximal independent set problem. Ruling sets may only become easier as alpha decreases, since alpha is a distance lower bound. In fact, for example, a solution for a 5-beta ruling set is also a valid solution for the 4-beta ruling set problem. And observe that if one proves a lower bound for 2-beta ruling sets, they directly apply to larger values of alpha. On the other hand, since beta is a distance upper bound, the larger is beta, the easier the problem may become. In fact, a solution for the 2-1 ruling set problem is also a valid solution for 2-beta ruling sets, with beta larger than 1. Hence, MIS is the hardest 2-beta ruling set. Therefore, understanding 2-beta ruling sets is strongly connected with understanding MIS. What did we know about MIS prior to this work? We discovered in 2019 that for deterministic algorithms, MIS requires omega of log n over log n rounds. This result follows directly from a lower bound of the same complexity for the maximal matching problem. The reason is that computing a maximal matching of a graph G is equivalent to computing a maximal independent set in the line graph of G. The line graph H of a graph G is constructed as follows. We put a node H for each edge of G, and we connect two nodes of H if they are connected to the same node in G. Hence, this lower bound for MIS does not hold on, for example, trees, but it only holds on line graphs. To recap, we wanted to understand 2-beta ruling sets, but we already knew that we could not just adapt the existing lower bound, since on line graphs it was known that 2-beta ruling sets for beta strictly larger than 1 could be solved very efficiently, that is, in just log star n rounds. So we were in the following situation. We knew that MIS is hard on line graphs. We knew that ruling sets are easy on line graphs. So we wanted to find a genuinely different lower bound proof for the hardness of MIS that could also be extended to ruling sets. For this purpose, we needed to find a lower bound for MIS that did not exploit the hardness of maximal matching. The most promising technique that we had at the time, and that we still have nowadays for proving lower bounds in the local model of distributed computing, is the so-called automatic round elimination technique. With this technique, we are able to show lower bounds that hold even on trees. So our goal was to understand the MIS problem directly on trees through round elimination. And I'll just very briefly mention the high-level idea of the automatic round elimination technique, which is the one that we use in this work with some additional ideas. The round elimination technique gives us a way to take a problem P and define a problem P prime that is exactly one round easier than P. By applying this technique multiple times, one can then try to analyze the obtained sequence of problems and infer the asymptotic behavior of the original problem. Unfortunately, it is not actually that easy to apply this technique because every time we apply it, we obtain a problem that is doubly exponentially larger than the original one. And this makes it extremely hard to analyze how a problem behaves under this technique. Now, not all problems behave in this way, and some problems instead have a special property. Some problems satisfy that the result of applying the round elimination technique on them is the problem itself, and we call them fixed points. Now, this may seem counterintuitive because it would imply that the problem is at least one round easier than itself, which is not possible. But actually, for technical reason, this can actually happen, and we know that when this happens, this implies that the problem is in some sense hard. In fact, we know that if a problem is a fixed point, then it requires omega of log n rounds for randomized distributed algorithms, and omega of log n for deterministic ones. And there are some interesting problems that are fixed points. For example, the problem of orienting the edges of a graph such that each node of degree at least 3 has at least one outgoing edge. That is called the Sinclair's orientation problem. If we apply round elimination on this problem, we again obtain the Sinclair's orientation problem as a result. And while we know already that delta coloring requires omega of log n for deterministic algorithms and omega of log n for randomized ones, we also know that this problem is not a fixed point. In fact, by trying to apply the round elimination technique on delta coloring, we really see this doubly exponential growth that I was mentioning earlier. But now one may ask, can we relax the delta coloring problem and obtain a new problem that is easier and that is also a fixed point? But one may also ask, why would we care about that? We already know a lower bound for this problem, and a fixed point would not give any better lower bound. So let me explain why we really wanted to have a relaxation of delta coloring, which is a fixed point under the round elimination framework. In order to apply round elimination, we need to encode the problem in a very specific way, by listing its node and edge constraints in a very specific language. I will not go into the details here, but MIS can be encoded as follows, on graphs of degree 4, for example. Nodes are either in the MIS or not. If they are in the MIS, they are required to output M on all their incident edges. If they are not in the MIS, they have to prove that they have at least a neighbor in the MIS by outputting P on an incident edge, connecting them to a node in the set. The edge constraints are not listed here, but for example, if an edge is labeled P by a node, then on the other side there must be an M, meaning that a node outputting a P has a neighbor outputting M, and hence in the MIS. So the node constraint of the MIS problem can be simply written as two possible allowed configurations. One is MMMM and the other is PUUU. Now just imagine to see the line MMMM as a color, let's say color M. And as already discussed, we can see the second line as a pointer P. We then realized that by applying the round elimination technique on the MIS problem, we would get a new problem where there are the old allowed configurations plus an additional line that can also be seen as a color, in this case color A, plus some additional lines that have no real intuitive meaning. Let's call them garbage. And then, by applying round elimination again, we would get an additional color, color D, plus a lot of garbage. And in fact, we noticed that this garbage grows doubly exponentially. Unfortunately, in order to prove a lower bound for MIS, we needed to characterize how this obtained garbage behaves, which looks like an extremely challenging problem. So very intuitively, we observed that the problem that we get after applying round elimination for k times is the following. There are k plus 1 colors, there is the pointer line, and there is a lot of garbage, a huge amount. Then we also realized that this garbage looks like the same as the garbage that we get if we try to apply round elimination directly on the delta coloring problem. So we then realized that understanding delta coloring is a necessary step in order to understand MIS. So let's recap. We wanted to understand delta coloring in order to better understand the landscape of LCLs and close some open questions related to distributed complexity theory. For this reason, we started to study ruling sets because they are used as a subroutine in the current best delta coloring upper bound. In order to understand the ruling sets, we first tried to focus on MIS, because it is the hardest to beat a ruling set. But for understanding MIS, we first had to find a way to prove a lower bound for delta coloring through round elimination, because somehow the delta coloring problem appears as a sub-problem in the lower bound sequence of MIS. Notice that at this point, we knew that understanding delta coloring was necessary to understand MIS, but we did not know if it was actually sufficient. So back to the question, is there a fixed point for delta coloring? And the answer is yes. The idea is that we can define a relaxation of the delta coloring problem that is a problem that is at least as easy as delta coloring, such that if we apply round elimination, we get the problem itself. I'm not going into the details here, but the idea here is to define a problem where nodes may output multiple colors instead of just one. For example, outputting colors A and B at the same time. And if nodes are multicolored, then they are rewarded by allowing them to have some neighbors of the same color. For example, a node colored with both A and B may have one neighbor that has also color A. Now the cool part comes. MIS is an easy problem in the sense that it can be solved in log-star rounds on bounded degree graphs. Delta coloring, and in general K coloring for any K at most delta, is a hard problem in the sense that it requires omega of log n for deterministic algorithms. What we did in order to prove a lower bound for MIS, and in fact for the whole family of arb-defective colored ruling sets, is to define a relaxation of the problem, in the example MIS, where we also allow the additional configurations that make the K coloring problem a fixed point. Or in some sense, we embedded a proof of the fact that K coloring is hard inside the MIS problem. Curiously, by doing so, we obtain a problem satisfying that, if we apply round elimination, it does not grow exponentially, but it gets just slightly larger, which allows us to exactly characterize its behavior under round elimination and prove a lower bound. So this is the whole idea of our approach. Let me conclude with some open questions. The first one regards the delta coloring problem. The best lower bound is log n, while the best upper bound is log squared n. Can we find a better algorithm, or can we improve the lower bound? The other open question is about fixed points. As we have seen, fixed points play a crucial role in proving lower bounds in the distributed setting. And the question is to understand whether all problems that require omega of log n have a relaxation that is a fixed point. I hope you enjoyed the talk. Thanks for your attention.